All right, so this is part 2 of our 2.3 solving absolute value inequalities. Today we're looking at how to solve them algebraically. Yesterday we looked at the graph and looked at what are the possible solutions when we're graphing them to solve. And now we're going to see what that looks like in terms of algebra. So some things that we're going to have to remember about our inequalities is something we learned once upon a time when we were solving kind of more basic inequalities. And if you remember that if we have a situation, let's say we have 10, and this is just kind of an example, and we'll talk about how it ties the problem in a moment. And we know that 10 is less than 12. So let's say we go ahead and try, doing different things to this expression. We looked at before how we could add them and that add something to both sides, and that's not going to change our inequality, right? We know 11 is still less than 13. And then if we multiply by something, it will also not change our inequality. So that's 26. So 22 would still be less than 26. But what happens if we multiply by something that has a negative number attached to it? So what if we multiply both sides by a negative 1? What happens to our inequality? We get negative 22 and we get negative 26. So we know on the number line that negative 22 is actually closer to 0. So this is the greater value. So what we notice is that when we're multiplying by a negative number, we actually need to switch our inequality sign. And remember, that works also for dividing by a negative number. Anytime we're multiplying or dividing by that negative number, we have to switch the inequality sign. So this is something I wanted to remind you of that you've learned once upon a time that we're going to use today. So what this will look like is we are going to solve and graph, but the graph will look different than what our graphs did yesterday. So solve and graph. Our first inequality we're going to look at solving is the absolute value of 4 minus x plus 15 is greater than 21. So we're going to treat this the same way we did solving regular inequalities. So we're still going to isolate our absolute value, regular absolute value problems. We're still going to isolate our absolute value. So we'll subtract 15 from both sides. And we get the absolute value of 4 minus x will be greater than 6. So at this point, we know, okay, so there's two possibilities. We know that this difference can be equal to 6 because the absolute value of 6 will be greater than 6, or this can be equal to negative 6, or I guess less than negative 6. So when we do that, let's go ahead and split it and see what that will look like. So we have 4 minus x is greater than 6. And we know that if we're writing this expression and we're introducing a negative on the right-hand side, we know that for this to be true, we have to switch our inequality sign. So this happens in a couple different places, right? We have to make sure when we're actually doing this in the problem that we are switching signs. And then also when we're introducing this negative form of our solution, we also need to switch the signs. So I'm just going to try to highlight it without making it too smudgy. So we know that we have to switch this sign because we have that negative 6. So that will be something to make sure you remember. That's an easy thing to forget. Okay, so this will be the same sign. We just are removing the absolute value. But when we introduce that negative, change the sign. So from there, we just go ahead and solve. So negative x is greater than 2. So we have a negative 1 coefficient. So let's go ahead and get rid of that by dividing. And we are dividing by a negative. So again, we'll switch the sign. So that will be less than negative 2. So right here, why I switched the sign, we have negatives we're dividing by. So we have to switch that sign. We'll do the same thing to our second inequality. If negative x is less than negative 10, we have to divide by that negative 1 coefficient, and we are still going to switch the sign. So your sign can switch lots of times. It won't always switch. It just kind of depends on, I guess when we're solving, it won't always switch. It just depends on what the equation is like or what the inequality is like. Okay, so let's kind of look at what our solution is. So we have something, an x that is less than -2, and we also have to be greater than 10. So think for a moment, are there any numbers out there that are less than -2, but at the same time, they're greater than 10? And if we think for a moment, we go, no, like that, you can't do that. You can't be less than -2, but still be bigger than 10. So this is going to be one of those situations we talked about yesterday. That's going to be an or. Okay, and if we graph it, we'll see that, oh, it definitely looks like that or situation. So when I graph it, I mean, we're going to graph on the number line, kind of like we did when we first were solving inequalities in middle school or in Algebra 1. So on our number line, we're going to go ahead and just add the values we need. So -2, but we have to make sure they're equally spaced because that's what makes it a number line. You can't just skip a bunch of numbers. So here we have a number line. We make sure we have -2 and 10 on there. We want to fit both of them. And we know our x values are less than 2, but they're not equal to, right? There's no equal to -2 going on here. They're just less than -2. So to graph this, we know it's non-inclusive at -2, so it's an open dot. So we're like that little bubble's protecting -2. We can get really close, but not actually get there. And then it can be anything less than that. So we'll point to the numbers that are less than -2. And, or I should say, or we know that our numbers are non-inclusive to 10, and they can be greater than 10. So this is why, again, it looks like an or, because we can be over here, or we can be over here. We can't have a number satisfying both of these situations at the same time. That's not possible. So this is the kind of graph we're talking about. The reason why we know it's a single variable is because we're only given an x. We're not worrying about that second dimension, that y. We're not splitting this up to graph it on a coordinate plane like a system. We're just graphing the actual solution to this inequality. So let's look at another example. And I'll jot it down for you. We're still going to solve and graph. And the inequality is the absolute value of x plus 4 minus 10 is less than or equal to -2. So we're going to do the same thing because we're solving an absolute value inequality. We're still going to isolate this absolute value expression. We know that we can break apart our absolute value inequality to solve two separate ones. Let's start with the positive one because that one's the easier one to write. So x plus 4 is less than or equal to 8. So we didn't change anything because the number just stayed the same. So the sign can stay the same. And then for the second one, we are going to solve with -8. So for that other possible answer, so we know we have to switch the sign. So whatever direction it is right now, we're just going to flip it. And I'm going to highlight that just to make sure we're drawing attention to that whole switching process. And now we just solve. So now it's the part that's kind of straightforward. So x is less than or equal to 4. And here x is greater than or equal to -12. So now let's think about this. We have a number that's less than 4 and a number that's greater than -12. So if you think for a moment about what could be in that range, less than 4. So let's see, that could be 0, that could be -1, that could be 2, but it has to be greater than -12 at the same time. So I can think of a lot of numbers. I can think it would be greater than -12, but less than -4. So this is going to be an and, because we can satisfy both of these solutions at the same time. And if we look at what this will look like on a number line, it makes sense that we call this and. So we have less than -4, and this is inclusive. So we have that equal to. So we can put a closed dot at 4, and it's going to be anything less than that. So we are going this way, right? Anything less than that. Okay, I'm gonna just leave my line going there. And then to graph my other end, so I know this goes on forever and ever and ever and ever this way. From my other end, we know it's going to be greater than or equal to negative 12. So we're going to put a closed dot at negative 12, and we're looking at all the values that are greater than it. So we can kind of see, oh, it'll be this range right in the middle, or this interval right in the middle. So we know it's less than 4, less than or equal to 4, but then bump, we're going to be greater than or equal to negative 12. So our ands will always be kind of this inclusive interval. Not necessarily inclusive on the endpoints, but it contains all those values between. Remember, this is, we can also think of this as between those two values. And or remember, we're satisfying either one end or the other end. So the graphs look very different, kind of like they did yesterday when we were actually just graphing to solve. So let's go ahead and write this so it's one inequality. So remember, we think of it as between. So how we can write that as a solution is we know we have x. So I'll write this in pencil. We have x is in between negative 12 and 4, and that's inclusive on those endpoints. So we know it's going to be between negative 12 and 4.